So there's no questions on the attendance homework?
I'm confused on Wednesdays.
Yeah, that was a tough one. I had put it up because I copied it from the book and then like, but then I figured if we are going to go over it anyways, is everyone okay with the first two?
Yeah, I think I did those right.
Okay.
Can we go over Tuesdays?
Let's just go over all of them so we make sure. If two fair six-sided dice are rolled, what is the probability that the dice shows the same number? So the first thing you want to know is how many outcomes there are. Remember, outcomes, because rolling a die, the first roll doesn't affect the second roll. Each time there are 6 possibilities, a 1 through 6. So there are 36 possibilities. That's your total. You always divide by your total. If we want to find the probability they're the same number, how many cases are there when you roll it, both numbers would be the same? Anyone? Rather than me writing all of them, we'll just find a picture on the internet. So this is the 36 possible outcomes, and we listed them last class. Notice the doubles. There's 1, 2, 3, 4, 5, 6, and there's only 6. So there's 6 out of the 36. And you could have left it like that, or you could reduce it by 6, dividing top and bottom by 6. It's 1/6. I would not use the decimal or the percent simply because then you'd have to round, but it wouldn't be wrong. 1/6. Because the 6 keeps repeating. I guess this would be equals to, because that's, remember the line over top means that value keeps repeating. So any one of those are fine. I like this one because it's an exact value. These two we have to round. Any questions on it? For the next one, what is the random probability? What is the probability that a random chosen human being is an American? Well, a random human being would be everyone in the world and Americans. So we'd need to know the population of the United States and a population of the world. And that can be an estimate, or you could have looked it up. Let's do the United States first. What's the population of the US?
When I looked it up, I got 336 million, I think.
Okay, yep. Somewhere between 330 million and 340 million. Yep. And what is the approximate population of the world? Anyone? You can look
I-
it up. Oh, go ahead.
I had gotten 7,888 billion.
7.8 billion.
Yeah.
Now, when dividing these units are not the same. So you either need to put all the zeros in there or make them both the same. I would probably just put the zeros. So that would be 336 million. 7.8. That's 1,000, a million, a billion. Any questions? So that would be your fraction, or it can be reduced if we can cancel these zeros. And then divide them to get your decimal. Okay. Oh, I didn't put any answer. So I rounded 3 decimals. That way when I found the percent by multiplying by 100, I had a decimal place. So 4.3% of the world is Americans. Any questions on that? Okay, this one was a little tough, and I accidentally wrote on here instead of my other paper that we could write here, but suppose that 10,000 barrels of nuclear waste are household in a storage facility. So 10,000 barrels. Each barrel has a 1 in 100,000 chance of a leak each year. If leaks in different barrels are independent events, what is the probability that at least one barrel develops a leak over a 20-year period? So remember, what they mean by independent is one doesn't rely on the other one. If one leaks, it doesn't mean that others will leak. So kind of like drawing a card. When you draw the second card, if you don't put the first card back, it changes it. In something like this, it could be, well, if one is leaking, there's a defect, which means another one has a defect. They're not, each one is independent. So just because one has a fault and leaks doesn't mean another one does. And that's why they're telling you they're independent. So we could find the probability, wait, it was a leak, right? Yeah. The probability of a leak in one barrel. Well, the probability of leak is 1 in 100,000. You could keep it as a fraction, or you can use the decimal, whichever one you want. So that's the probability of barrel leaks. Now we want to find out at least one barrel in 20 years. So we'd have to see one barrel and then we'd have to do 2 barrels. Then you got all the different barrels because there's 10,000 of them. It's a lot of different possibilities. But it's easier if you take 1 minus the probability of the complement, 1 minus the probability none of them leak, because that's only one case. There's only one way that none of them leak. Whereas at least one, you got to look at all 10,000 barrels. And so there's a lot of different possibilities. So we want to find the probability that none of them leak first. So first we'll find the probability that one barrel does not leak. Remember, the probability of the complement is 1 minus the probability it will. So the probability it won't leak is 1 minus the probability of its complement. Oops, I'm missing a 0 in them. 1, 2, 3, 4 zeros. So the probability that one barrel will not leak is 0.99999. Now you could do the 20 years for one barrel, or you could do all the barrels first. I did one barrel. One barrel. I would never ask this. This will not be asked on your test unless it's on the take home part and we do it ahead of time just to look at something like this again. This first part I could see, but I think it gets a little too involved with some of the rules. And then if you look on the chat, the AI program or Chegg, they use binomial theorems, which we don't get into in this course. So if you looked it up on there, there's 3 different ways they show you. I don't know. I like to look at those things to see what I can expect from students. 1 barrel, no leak for 20 years. Now remember, these are independent, so I can take this answer, the no leaks, and keep timesing it by itself 20 times. So 0.99999 times 0.9999, 20 of them, because they're independent. Or you can take it to the 20th power. Because if you multiply something times itself, that's the number squared. 3 times cubed, 4 times to the 4th, 20 times to the 20th. So we can take that 0.99999 to the 20th. Any questions on that? So that's one barrel won't leak for 20 years. We want to take the probability that 10,000 of them will not leak for 20 years. Just like this one, you're going to take this and multiply it times itself 10,000 times. Now this one I didn't figure out. I just wrote it like this. That way I wasn't getting a bunch of decimals rounded. Any questions so far? So the probability that at least one of the 10,000 barrels leaks in 20 years is 1 minus the probability none of them leaks. This is the probability that none of them leak. So it's 1 minus 0.9998 to the 10,000. And I just didn't calculate this because then I'd have to round. I just figured plug it in here. But you could have calculated it first. But I thought it was important to understand this answer also, and that's why I wanted it somewhere. And I thought homework was better. When we bury 10,000 barrels of a nuclear waste, there's an 86.5% chance that at least one of them, if not more, is going to leak. That I think that's too high to be burying them. But because 20 years is not a long time. But that's what this is telling you, that there's an 86.5% chance that if you bury 10,000 barrels of a nuclear waste in 20 years, at least one of them will leak. Any questions on that? How about Fridays?
I haven't done that one yet.
Okay, let's look at it. I'm sorry, I have a student taking an exam with an assistant and they had a question. Okay. The board game Discworld uses a 12-sided dodecahedral die. Unfortunately, I lose the special die, but I still want to play the game. Someone suggests that using a pair of ordinary 6-sided die instead and then adding their scores. What do you think of this suggestion? So we have one die. Well, I'm drawing a cube, even though it's going to have 12 sides. It has the numbers 1 through 12. Or we use 2 die. Instead. Do you think it's a good idea? Like if we roll 2 die and add them together? Will this represent all of the values that this 12-sided die does?
No.
You're correct. Which one would be missing?
Well, I was thinking that like it wouldn't have all of the like numbers, like, but I'm not sure.
No, you're right. The only one really missing is the ones, because if you roll 2 ones, you get a 2. So when you're rolling 2 of the die, when we roll 2 of these, the smallest we can get is a 2, because we can get a 1 on one and a 1 on another, which adds to 2. So we'll never get a 1. So that's one problem with the die. Like if you think of the game, I don't know if you know the game, sorry, but you have to roll a 1 or a 2 to get out. Well, then if you're using a 12-sided die, you can get a 1. If you're using 2 die and adding the sum, you'll never get a 1. So then you have less chance of getting out of the base. And so if 1 is needed for the game, that could be a problem. So one of the problems with using the 2 die is that you will never get a 1. You will get all the other values, because we can get a 2 here. A 1 and a 2 will give us a 3. A 1 and a 3 will give us a 4. A 1 and a 4 gives us a 5. 1 and 6 gives us, whoops, 4, 5. I skipped 1. 1 and 5 will get us a 6. 1 and 6 gets us a 7. 8. A 4 and a 4. 9. So all of these are possible. Now there's more than one way of getting some of them. A 4 and a 5. 10, a 5 and a 5. 11, a 5 and a 6, and a 6 and a 6 will get us a 12. So we could get all of the numbers. Now some of these have more than one way of getting them, but we can get all of them except for a 1. Are all the values, so that first question, are all the values of the 12-sided die represented? Everything except for the 1. So it's not a bad idea, depending on how the 1, if it's needed for special things. Think about the probability of rolling a 7 on the 12-sided die. What's the probability of rolling a 7? With the 12-sided die? Anyone? On the 12-sided die, there is only 1 of every number. So there's only 1 7 out of the 12. Then we could write it as a decimal or a fraction. If you want it's 0.083333. That way we could look at the comparison. How about when we're rolling this, the probability of getting a 7?
It would be more than one because there's like multiple ways to add up to 7, like
Yep.
both of the dice.
And I'll bring the dice up again so we can look at it. So to get a 7, here's 1, here's 2, 3, 4, 5, 6. Now a 1 and a 6 and a 6 and a 1 are different because they're 2 different die. So there's 1, 2, 3, 4, 5, 6 different ways of rolling. 1, 2, 3, 4, yeah, 6. 6 different ways out of the 36. 6 divided by 36. So you have a higher probability of getting the 7 here than you did there. So your probabilities when you're rolling are different. You're going to, 7's actually the highest. If we look at the die again, getting a 2, there's only 1. Getting a 3, there's 2. Getting a 4, there's 3, a 5, and it goes up. If you remember, we wrote these probabilities last class. And then the 7 has the most, and then it goes down again. That's why in craps, I think it's if you roll the 7, then the game's done. And I think you lose if you roll it first. I forget. I always have to look it up because it's not something I play a lot. But it's the most likely one to come up is when you roll a 7. 17% chance. But so that's why in craps they use the 7 for stopping the game, because it should come up the most often. And so then you're just writing about it, but I just wanted you to think about it because it sounds like a great idea. If you lost this one, it's probably cheaper to get 2 die, and you probably have them laying around somewhere. But you're not going to get the number 1. So if that's important, it wouldn't be a good idea. And the probabilities for rolling are not equally likely. Here, each number is equally likely. Here, they are not. And it's just making sure, like having you explain things in words. Any questions on it? It also, I don't know if I put it on here. This was in the book, but I really liked the question. It also asked if there was another way you could think of using the 2 die. But I couldn't think of another way. Like adding, you're getting everything but the 1. If we multiply, we're getting a lot of numbers that we wouldn't get here. Because you figure 2 times each value, 2 times 6, well, 2 times 6 would work. 3 times 6 is 18, 3 times 5 is 15. There's a lot of numbers that there's so many more numbers that we wouldn't need. Can anyone else think of another way? I couldn't think of one other than adding that would get me as close to 12 numbers as possible. I don't know. No, I mean, if you can think of something else, let me know. My mind's just not thinking of it. Maybe the 1 die is 1 through 6, and the other die, I guess that's what we could do. Like the one I showed you with the red and the green. Red could be 1 through 6, and then green Yeah, but still you're not, that wouldn't work. I was thinking it could be 7 through 12, but you're rolling both of them, so that wouldn't make sense. I don't know. But if you think of another way, put it on there so then I can think about it. Any questions? Okay. 5.3. It's the payoff from a lottery ticket is a rather complicated random variable. So we're thinking about expectations and payoffs. Whether we like depending on what the payoff could be. Let's illustrate the idea by drawing a diagram for a simpler random variable rather than a lottery ticket, because a lottery ticket is a lot of values you need to get. A bet on a coin flip. Suppose that a coin is flipped and I stand to win. So this is our win. Where W is $10 if the coin is tails. So if I get tails, I win $10. But nothing if the coin comes up heads. Heads, I get nothing. So that's one way of showing your sample space, and we'll put it in a frequency table. But W is a random variable based on the flip of the coin. So our sample space was tails and heads. W was our winnings, and they'll use different variables. Usually they try and make the variable stand for something. In this case, W for winnings. Consider a random process with sample space. A random variable X associated to this random process is a function from S to the set R of real numbers. So tails is going to 10, heads is going to 0. They're taking that or qualitative data and making it numerical. Put differently, a random variable is a numerical value that depends on the outcome of a random process. So the $10 depends on if you toss a tail or heads. Here's another example, a random variable for which the underlying random process is the rolling of the die. We decide to name this random variable X. Now, if you want, you could have your squares here. If X dollars is the payoff for a bet, then I pay you $10. If you roll a 2, 3, or 5. So we have the $10 is for a 2, a 3, or a 5. You pay me $20 if the number is a 4 or a 6. Yeah, we pay him. So this is what we get. If you roll a 4 or a 6, you pay out $20, and that's why it's negative. If the number rolled is a 1, there's no payment either way. Would you like the bet? Well, there's different things to think about. If I roll a 1, nothing happens. I didn't lose anything. If I roll 2, 3, or a 6, that's half the numbers on the die. 3 out of 6. I get $10. But if I roll a 4 or a 6, I'm losing $20. There's a minus sign. I don't know. Is it worth the loss? That's a big loss. Well, what we can do is find what's called the expected value or expectation of a random variable. They write it E of X. you list all the values of the random variable can take. These are all the values it can take. Multiply each value of probability by its value. So they're saying take the dollar amount that it makes and multiply it by its probability. Add them all up, and that's your expected value. And I'll show you, we'll do this problem. I think that's the one I wrote. Yeah. So if we roll a 1, we get nothing. 2, 3, or 5, we get $10. 4 or 6, we lose 20. So the next thing you want to do is find the probability of each of those. It's up to you if you want to write it as a fraction, a decimal. I like to keep, because we're dividing by 6, we get lots of decimals on this problem. I would prefer the fraction then until the very end. That way you're not rounding. The probability, if we have a die, what's the probability of rolling a 1? There's 1 out of the 6. What's the probability of rolling a 2, a 3, or a 5?
3 out of 6.
There we go. Yep. And the last one, a 4 or a 6?
2 out of 6.
Yep. And notice your probabilities should add up to 1. 2 plus 3 plus 1 is 6 over 6, which is 1. Contributions you multiply across. 0 times 1/6 is 0. 10 times 3/6 is 30 over 6, which I'm going to leave the fraction. And multiplying the last one, negative 20 times 2/6 is a negative 46. The expected value, you add up the contributions. $30 minus 40 divided by 6. I went 2 decimal places because we're talking about money. When you play this game just one time, on average, you will lose $1.67. Doesn't make sense because, like, look at these bets, but this is in the long run. So if you play it several times, you're going to be, it's a game of that has a loss. If it were positive, it would have a win. If you play it 1,000 times, and multiply by your expected value, it will tell you how much you should win in the end. So 1,000 times 1.67. If I play this game 1,000 times, I'm expected to lose $1,670. Now, if you just play it once and you lose, you need to quit. If you play it once and win, then you feel lucky. Maybe you want to play it again. So if you played it once and win, you get $10. If you play it again and you lose, you owe 20. So you have the 10 that you won, but then 10 of your money. So you're technically only losing 10 if you won the first one and lose the second one. But in the long run, this game, it is a game of loss because it's negative. Any questions on that? Definitely. Gambling is a game of loss. Near where I live in Pennsylvania, there's one called Mountaineer, and they have a wheel. And I like to play that wheel because most of the things on it are $1 or $2. And so you always the biggest chance. And then there's one, there's like maybe 100 on here, but there's one of them that's a $50 win and one is a $100 win. Everything else is a 1 or a 2. And so they have the bills here, a $1, a $2. I think there's a 5 and a 10, but they don't hit very often, but they hit more than the 50 and the 100. What I do is I choose one of these and maybe put my coin there. And then I choose here and here. So then I'm either getting one of them back or 2 of them back. So here I'm getting an extra one, I'll have $2. If I bet $1, I'd have 2. If I bet here, then I'd get $4 back. This is most likely to happen, but every once in a while, this one comes up and then you win 50 of whatever you bet or 100. But by knowing that this comes up most often and keeping a coin on one of those or both of them, then you're getting most of what you bet back. So then you're not losing as much as you would if you just kept putting it on the 50 or the 100. But I like to play that one to see how it goes. But I have to go, like there's certain hours where it's double what you normally would pay. And so then I don't like to play it. But just because it's a game of chance and I like probability. And I just alternate these to see what happens and where it lands. And then if I hit this one, then I get to go to dinner. And it won't cost me anything. But here you're winning it back. And so you kind of want games like that. This one, that's not happening. Like there's not that extra safety net. So if you look for those wheels, those are where you usually, you're not going to win huge amounts, but you're not going to lose huge amounts either. You can just sit there and play for a while and see what happens. Any questions on that? If we have time, well, let's stop there. That's a good stopping spot. And we'll talk about large numbers next class. Is there any questions on anything?